Hello everyone, and welcome to the first video of Unit 3. In our last unit, we examined constant velocity motion. Right? That was the motion that was exemplified by the toy car. And we looked at many different ways to represent that constant velocity motion. We represented it with position versus time graphs, velocity versus time graphs, motion maps, and even the odd equation or math model. But one thing that we didn't do is we didn't at all try to explain why things move with constant velocity. And so that's what we're going to do in this unit. We're going to look at why do things move at constant velocity. And to do that, we need to introduce a new idea called force. So we're going to define force as an interaction between two objects resulting in a push or a pull. And the first part of that sentence is key. Push or a pull probably isn't too surprising to you, but we're going to define all forces as interactions. And to have an interaction, you've got to have at least two objects. And so you're going to see here at the beginning of the unit that we're going to look at forces in terms of the interaction which causes the force. So let's start out with a little example here. By the way, this one will be called types of forces. Here's a water bottle. It's just sitting on a table. So we want to represent all of the interactions and the forces that arise because of those interactions. And to do that, we're going to use a new representational tool called a system schema. This is a visual representation, a way of visualizing all of the interactions and the forces that are occurring. So again, it's a visual thing here, which should help us see what it is. And it's very useful here at the beginning. And maybe we won't do this forever, but we'll do it at the beginning of this unit in order to get a good idea of what interactions are actually occurring. So let's start out by having a representation of the water bottle. And I'm not going to spend a lot of time drawing here, so it's a water bottle, right? Is that circle. The question is, what does the water bottle interact with? What other objects are interacting with the water bottle? Or you could also look at this as, what forces are acting on the water bottle? Now that question, probably the first thing that you might say is gravity. And that's a good way to start. We usually start most of our force analyses that way. The question then is, what is exerting the force of gravity? Because again, every force is an interaction between two things. So it's being exerted on the water bottle. So what exerts the force of gravity? The entire Earth exerts the force of gravity. And so we're going to represent that interaction. See that little red thing there is the interaction. And we're going to label it with the kind of force that occurs. And again, that force is what we're going to call the force of gravity. Now, a couple of things about the force of gravity. First of all, our symbols. We're going to call all forces capital F, and the subscript will tell us what kind of force or what kind of interaction is going on. So force of gravity is F sub G. And this is kind of a different way of doing things. Some people would use a capital W or a big G or different things for force of gravity. All right, but we're going to use capital F for all of our forces and then a little g to tell us what kind of force. And notice there is an arrow over it because it is a vector quantity. Pulling on something in one direction has a different effect than pulling on it in a different direction. Now, gravity is kind of an interesting force because you don't have to actually be in contact with the Earth to have a force of gravity exerted on you by the Earth. For example, if I took that water bottle and held it up in the air and let it go, it would fall. Why? Because the Earth is pulling on it, because of the force of gravity, even though it's not touching the Earth. So gravity falls into a category called a long-range force. Other ones you might have experienced would be like magnets. You don't actually have to touch two magnets together to have a force between them. And gravity works that way. Right? So this is a long-range force exerted by the Earth on the object. So in our system schema, we're going to write the F of G. So there's the relationship. Now, is the water bottle interacting with anything else? I mean, think about it this way. If the water bottle wasn't interacting with something, gravity would make it fall. Right? Like, picked it up and I held it in the air and I let it go, it would fall because of gravity. So something has to be holding up the water bottle. If you look at the diagram, that something is the table. So there is an interaction here with the table. Again, we're going to represent it with a little red line. Well, that force is coming from a support force from the table. And support forces are given special names. They are called normal forces. Capital F with a capital N subscript. Okay, this is a normal force. A support force. And this is a little weird to think of an inanimate object like a table exerting a force. But if you're in class, you're going to see a little bridging activity where I'm going to try to convince you that an inanimate object essentially compresses when you put something on it. If you think about it from a microscopic level, there's all the little molecules, and the little molecules exert electromagnetic forces on one another like little springs. And if you put the water bottle on it, it'll compress it a little bit and it'll push back. It's kind of, if you want to think of it this way, a crunchy kind of force. You're crunching it together and it's pushing back. Now, one thing about a normal force is that it always acts perpendicular to the surface. So where does this word normal come from? Why do you call it a normal force? Why not call it support force? Or even perpendicular force? Well, if you take enough mathematics, the word normal actually has a meaning in math. Normal means perpendicular to the surfaces. So rather than saying, hey, this is a support force perpendicular to the surface, we can say normal force, and that means the same thing. It's something you're going to have to get used to. It's a new terminology thing. So there's F of n. Now, are there any other interactions going on here? Well, if you think about the table, is the table interacting with the Earth? Sure. Right? The table has weight. It's being pulled on by the Earth by another force of gravity. Is that gravity making the table fall? It's being supported. What's supporting the table? Well, the floor is supporting the table. And so there'd be an interaction between the table and the floor. And since that's a support force, that would be a normal force. So there's all sorts of interactions going on here. And we're not even going to get into more complex things like air pressure or something like that. Right? So right now we have interactions between the water bottle and the table, the water bottle and the earth and the table and the floor. But we want to focus on the water bottle. So if we're going to focus on a single object here, we really only need the interactions that are with the object. So in other words, we're going to get rid of the interaction between the table and the earth and the table and the floor. Now, can you put them in your system schema? Sure. Is it wrong? No. Not going to lose any points or anything if you put them in there. You've just got extra interactions that aren't really going to be part of the problem because they're not interacting directly with the bottle. The floor is interacting with the table, not with the bottle. So notice now, if this is our system boundary, the little dotted line, this is what we're looking at, then we have two interactions that occur through the system boundary, and therefore we'll have two forces acting on the water bottle. And eventually we're going to get another way of describing those two forces, of visually picturing those two forces. But today we're going to stick with system schema. So here's a second example. This time, there's my hand, and I'm going to pull the water bottle across the floor at constant velocity. So something like this. Watch and listen again. So pulling the water bottle across the floor at constant velocity. So let's draw our system schema. Again, we have the water bottle. What is the water bottle interacting with? Well, as it was before, it's interacting with the Earth. There is an interaction there which we call a force of gravity. Is the water bottle still being supported to keep it from falling? Sure. In this case, there's not a table. It's being supported by the floor. So there's an interaction. And what do we call support forces that act perpendicular to the surface? We call that a normal force. Now, what else is the water bottle interacting with? Well, in this case, it's interacting with me. There's actually another interaction going on. You might have heard when you saw that water bottle being pulled across the floor, right? It's scraping against the floor. It's rubbing against the floor, right? And that rubbing is going to resist the motion of the water bottle. When surfaces rub together, we have a new kind of force, a new interaction between the floor and the water bottle, which we are going to call the force of friction. Capital F for force, little f for friction. The force of friction is a force which always opposes motion or attempted motion when surfaces rub against one another or move over one another. Friction acts parallel to the surfaces involved. Now, notice, therefore, there are now two interactions going on between the floor and the water bottle. There's a perpendicular support force, a normal force. The floor is supporting the water bottle, but it's also rubbing against the water bottle with a force of friction. Sometimes in physics we'll say things are frictionless, but you heard it scraping across the bottom. Right? So that's going to resist its motion. Now there's actually two kinds of friction that we have to worry about. There's actually many kinds of friction, but we're going to mainly in class deal with friction of surfaces that rub against one another, sometimes called sliding friction. We're not going to worry that much about fluid friction, okay, like oil or something like that. We're not going to worry about air resistance all that much. We'll talk about it a bit, but we're not going to calculate it and things. And so we're going to mainly stick with friction of surfaces which are sliding against one another. And in that case, there are two types. And it depends whether or not the surfaces are moving. So if the surfaces are moving over one another, we call it a force of kinetic friction. This is your first view of the word kinetic, although you might have heard that before in chem or something like that. Kinetic is Greek for motion. So this is literally the force of friction when the surfaces are moving. Okay, kinetic friction. And notice it's got an extra little subscript, F sub F K for kinetic. And then there's a different kind of friction if the surfaces aren't moving. Say I pull on the water bottle, but it doesn't move. There's still something resisting the motion. If it was on wheels, it would move whenever I pulled it. And what's resisting that motion is called the force of static friction. Static has a very definite meaning in science. When something's static, it means it's not moving. So if you think of a static electricity, for example, those are charges that are stuck. They're not moving on the surface. And if charges are moving, you have current. So static means not moving. So this is F sub Fs. Force of friction opposes attempted motion of the surfaces. So in this case, since we're pulling the water bottle across the floor, it is kinetic friction. See the extra little K there? You might want to add that to your system schema. So now, as we said, there is one more interaction going on, and that's me. I'm pulling on the water bottle. So I'm definitely making contact with the water bottle. Right? So what is that force? Well, we need a force name that is just very generic. And so we're going to use, in this case, what's known as an applied force, F sub capital A. So this is kind of what you call a force when you don't have a better name for it. Okay, this is a force which is applied to an object by a person or another object or something like that. You just call it F sub A. So there it is. So now notice, if we focus on the water bottle, there's 1, 2, 3, 4 interactions going on. The water bottle is interacting in two ways with the floor. It's being supported with a normal force, and it's rubbing against the floor with a force of kinetic friction. It's being pulled on by the earth, and it's being pulled on by me. So we have 4 different interactions, and therefore, we would have 4 different forces acting on it. All right, one more example. What would change about our system schema here if the bottle was pulled across the floor at constant velocity, this time by a rope? So this is supposed to be a rope right here. So I'm pulling on the rope, right? But the rope is pulling on the water bottle. So watch and listen again. So in this case, all right, it's moving at constant velocity. Well, let's see. Our beginning of our system schema doesn't really change. We've got the water bottle. It's being pulled on by the force of gravity between the water bottle and the earth. It's being supported by the floor, which would be an interaction we would call a normal force. It's being dragged across the floor, so they're rubbing against one another, and so that would cause a force of kinetic friction again because it's moving. This time, what else is the water bottle interacting with? Well, it's touching the rope. And so the rope is interacting with the water bottle. And when ropes or strings or wires or chains apply forces, they have a special name. You might have heard this before. It's called a force of tension, F sub capital T. So this is a force that's transmitted through a string, a rope, a wire, cable, chain, when it's pulled tight by forces acting from each end, right? There's a force of the rope pulling on the water bottle, and there's a force over here with me. Right? So that's a force of tension. Put on there. Any other interactions going on here? Well, I'm still there. But am I pulling on the water bottle? No, I'm pulling on the rope. So there's an interaction between me and the rope that would be an applied force. Well, if we're trying to focus on the water bottle, am I actually interacting with the water bottle? No, I'm interacting with the rope. The rope is interacting with the water bottle. So this applied force isn't really going to be part of our analysis of what's going on with the water bottle. And so there's now only 4 forces left. And we can actually get rid of that applied force from me. Again, if you put it on your system schema, is it wrong? No. Right? But when we're going to look at what's going to happen to the water bottle, we want to focus on interactions with the water bottle, not interactions that are 2 or 3 iterations away, the other things that are interacting. Like, we're not going to say, hey, the sun is pulling on the Earth and keeping it in its orbit. It's not really all that big of a deal to the water bottle. And so we can be a little discriminating here and try to focus our system schema, which will make the use of them later a little bit easier to do. I hope you enjoyed learning about some types of forces and system schema.